All right, so like we talked about in class today when we went over our vocabulary, prime factorization is, or if we're finding the prime factorization of a number, we are breaking down that number into a set of prime numbers which can be multiplied to result in the original number. Okay, and that's what we are going to start with today. And for both prime factorization and factorization, we are going to use what are called factor trees. They don't really look like trees, but we're going to pretend, okay? And so prime factorization. Let's come up with let's think of an example here. Let's use 28, right? So if I'm going to create a factor tree, I'm going to give my 28 two branches. And I got to think, what can I multiply to get 28? And in this circumstance, I'm going to do 14 times 2. And some of you might be wondering, but Ms. Ritter, what if you wanted to pick something different? And you can. We'll get there in just a second. So 14 times 2. I notice that 2 is a prime number. The only thing we can multiply to get 2 is 2 times 1, right? So it's prime. However, 14, so we circle it. 14 is not prime. 14 we can get by doing 7 times 2. Again, 2 is prime, so we'll circle it. And 7 is prime. The only thing we can multiply to get 7 is 7 times 1. So here we go. This is our prime factorization of 28 is 7 times 2 times 2. That is absolutely a correct answer. If you want to simplify it even further, you could write 7 times 2 squared because you have 2 2's. 1, 2 2's. Sorry. 1, 2, 2, 2. So we're going to put a 2 right there. 2 squared. Okay? But what if we had wanted to write it differently? What if we had wanted to say, hey, I know that 7 times 4 is 28. Is my answer going to be different? Well, let's see. 7 is prime, so we circle it. We're done with that branch. 4 is not prime, so it's going to get some more branches. 2 times 2 equals 4, right? Well, 2 is prime, and check it out. 7 times 2 times 2. Or, like we just said, 7 times 2 squared, because there are 2 2's. No matter how you slice it, that prime factorization is always going to be the same. Let's do another example here. Let's do 100. Well, I know that I can get 100 by multiplying 10 times 10, right? Neither 10 nor 10 are prime. So both of those are going to need branches. And I can get 10 by doing 5 times 2 and 5 times 2. Now here we go. Both 5 and 2 are prime numbers. The only way we can get 5 or 2 is by multiplying 5 times 1 or 2 times 1. So that's the end of this prime factorization. 5 times 5 times 2 times 2. Or there are 2 5s, so we could do 5 squared times 2 squared. We're going to do one more example like this to really talk about those exponents. That's what this guy right here is called, an exponent. What if we did 16? Let's find the prime factorization of 16. Well, I know that 16 is a square number because we get it. We're doing 4 times 4, right? 4 is not prime though. We can make 4 by doing 2 times 2, right? Well, 2 is prime, 2 is prime, 2 is prime, 2 is prime. So my prime factorization would be 2 times 2 times 2 times 2. I see 1, 2, 3, 4 2's. So I could say that this is 2 to the power of 4 because there are 4 2's. Okay? Really quickly, I just remembered that I didn't kind of show you this to make sure that it made sense. Let's do this out. If this is the prime factorization of 16, this should equal 16. 2 times 2 is 4. 4 times 2 is 8. And 8 times 2 is 16. There we go. So using factor trees, we can break down a number as far as possible to get its prime factorization. Now sometimes I'm just going to ask you for a factorization, not a prime factorization. And I'll say, how many factorizations can you find for a number? So let's practice that for a moment here. I'll give us a line, and let's just write factorization. So really quickly, let's factor out 32 all the way. And then we're going to use that. Let's use the number 32. Well, I know I can get 32 by doing 16 times 2. 2 is prime, so that branch is done. And then I can get 16 by doing 8 times 2. That branch is done. 4 times 2, that branch is done. And then 2 times 2. Those branches are finally done. So my prime factorization here is 2 times 2 times 2 times 2 times 2, right? That is 1, 2, 3, 4, 5 2s. So I could say 2 to the 5th power, 2 to the power of 5. However, that's not what I asked for. I just said, how many factorizations could we make? So let's take a look. We could do this right here, 16 times 2. That is a factorization. We could also do this one right here, 8 times 2 times 2. 8 times 2 is 16, times 2 is 32. We could do this one, 4, and then including all of those 2's, 4 times 2 times 2 times 2. Right? These are all examples of factorizations of 32. Okay? We could do, how else could we play with all these 2's? Could we do, I'm going to erase some of these lines to make it a little less confusing. Could I do something like this? 2 times 2 is 4, right? And then 2 times 2 times 2 is 8. 4 times 8, that's also 32. And we could keep going. So when we're thinking about factorizations, we're thinking, what are all of the different ways that we could make 32? And you could just think of the factors and write out a simple 2-number sentence, right? 16 times 2, 4 times 8. But you could also break apart some of those numbers. 8 times 2 times 2, give me a 3-number sentence. Or 4 times 2 times 2 times 2, give me a 4-number sentence. Okay? Let's do one more example of a factorization. Let's pick, I don't know, let's pick 27. How can we make 27? Well, we can make it by doing 3 times 9, right? 3 is prime, so we're done there. And then we can make 9 by doing 3 times 3. So there aren't that many options for this list of factorizations. We could have 3 times 9. We could have 3 times 3 times 3. And that's about it. Those are the only factorizations we can have for 27. Okay. I'm hoping this makes sense. We're going to talk about it as a group in just a moment. Way to go, guys.